Okay, guys, here we go. So, if you remember, we talked about, um, we're talking about simple harmonic motion. So let's look at a spring here. Spring mass system. And we want our equilibrium to be where it's centered. We'll define that x is 0. And so if we start, so this would be positive x hat. So let's say we stretch it over here, and this is our starting point. This is our amplitude, right? It's our distance A. That's going to be our amplitude. And what's going to happen is it's going to start there. We let it go. It's going to oscillate about that equilibrium. So it's going to go there, to the other side, come back, it's going to oscillate back and forth like that. And you know, this way is time because that's the way I'm going. If you flip that on the side, it looks like a sine or cosine graph. And again, look over those wave equation notes because it compares simple harmonic motion to circular motion. And remember we said our position graph looks something like this. And I'll throw this over here. Okay. Let's look at the anatomy of this real quick. This right here, this is your amplitude. So, we'll go over everything. Amplitude, this is angular frequency. That's, of course, time. This is your phase shift. And this constant right here, it's a vertical shift, but really it's like an equilibrium. This is your equilibrium. Usually we'll let that be 0. Okay. So right now we're gonna say phase shift equals 0 and our equilibrium's at 0. Because if you can see there, look, our equilibrium is definitely at 0. Because we define it that way, and that's how we usually would like to define it. So if our phase shift, just if you've taken, I mean, most of you guys are in calculus, so you've had pre-cal, but really this is the thing I assume you learned in pre-cal. If you shift it by, like if this was, just real quick trig, plus, I think it's pi over 2. Yeah. Yeah, pi over 2. It just shifts it to a sine graph. This would become negative, I think. Yeah, this would be negative. It's just a shift. It's kind of arbitrary, and we're not going to deal with that a whole lot. You can think of it really kind of as a starting position. I'm not going to say that because we have that equal to 0, but we want our equilibrium equal to 0. So anyways, we're just going to ignore those two things right now. So A cos omega t. Now at time is equal to 0, we have cosine of 0, which equals 1. So x of 0 is just our amplitude, A. So if you look over here at time 0, our amplitude is A. Cool. And let's say, so here we have omega. So if you remember, we'll go back to sine, a basic sine graph, sine omega t. It's gonna cross, so you sine, it's gonna look something like that, where this is pi, this is pi over 2, which is nice sometimes when we're looking at that. However, what I have over here, if you remember, omega equals 2 pi f. We talked about that briefly. Very briefly when we at the start of the semester. So what this graph over here on the left actually is, actually I think I phase shifted it. So these are actually, yeah, I actually phase shifted. It's a sine graph that's been phase shifted by pi over 2. So actually what this graph is, if you look, our amplitude here is 1. Down there's -1, so we're centered about 0. So our amplitude is 1. This is just sine. And what I did is I just did 2 pi f times time. Actually, this is phase shifted. Plus pi over 2, which is cosine 2 pi f times t. That's what this graph is, right? So I have this 2 pi built in. So rather one, oh, I think I said this wrong. One full rotation would be 2 pi. This would be pi. This would be 2 pi, right? So rather than have, it cross at pi and 2 pi, I think that'd be more useful when we're dealing with angles. But however, we're dealing with distance right now. So we kind of want to deal with regular frequency instead of angular frequency. So that's why we did it this way. So we can actually look at the graph and we can see what our frequency is. So you look at this graph. Remember, frequency is how many cycles per second. How many cycles in 1 second. And units are 1 over second or hertz. So this x-axis, that's just a legend. The legend is, this is in Python. I'm used to Mathematica, but I'm kind of relearning Python. So my graphs aren't as pretty and interactive as they normally are. But so this position, that's just a legend. But x-axis is time, and then y-axis is position. And the reason I have a legend onto here is because we'll talk about velocity and acceleration here in a moment as well. But so x-axis is time. So this is 1 second. It makes 1 revolution, or 1 cycle, I should say, in 1 second. So our frequency is just 1, right? And these are our variables that we look at. You can ignore all this garbage. But yeah, our frequency is just 1. I added this in there to show you if omega was just 1, this is what it would look like. So yeah, half a cycle would be at pi. A full cycle would be about 2 pi. Actually, I think it kind of cut it off there a little bit. So that's if our omega, our angular frequency, was equal to 1. But like I said, we just want to comment this out with normal frequency right now. And also, if you remember, frequency is 1 over the period. So I could have easily plotted something like this. 2 pi over the period times time. But I just decided to go with frequency. And likewise from that relationship, our time it takes to go one cycle is 1. So if frequency is 1, our period's also 1, because 1 over 1 is 1. All right. So let's look. That was weird. Someone just walked into my place. I should probably lock my door. It's awkward. Okay, so that's never happened before. I think they just went to the wrong place. Oh well, it happens. Anyways, back on track. Okay, so let's start with the simplest one first. So if we change our amplitude, so it's at 1 right now, change our amplitude to 3. So that means, we have our equilibrium right here, and we stretch it to an amplitude of 3. That's what we're going to start out with. So what our graph looks like, we start at 3, let go, it's going to go across the equilibrium, go to -3, so it's going to start here, go all the way over here, where this distance is 3. It's just negative because it's on the left side of our axis. And then it's going to come back and forth and back and forth, back and forth, back and forth. Simple enough. Okay. Now, again, I have this phase shift. You can just think of it as cosine, and the equilibrium 0, so you don't really have to worry about that. Let's change our frequency up. Let's change it to a lower frequency, 0.2. See what this looks like. All right, so if you look at this. Remember, our x-axis is time. So one full cycle is at 5 seconds. That's our period. That's the time it takes to go one full cycle. Remember, this is amplitude. This is going to be your amplitude over here, and this is going to be time. So one full cycle is 5 seconds. So t is 5 seconds. And we know this relationship, they're inversely related. So I typed in our frequency is 0.2. So 1 over 0.2, which that's 2/10. 1 over 2/10 is 10 over 2, which is 5 seconds. So when we look at this graph of position versus time, we're reading off the period, and from that you just 1 over it, 1 divided by 5 is your frequency, which is 0.2, 0.2 hertz, 1/5 hertz. And again, there's a lot more you can do with this. Those are the basics, so I'll just play around that. So if we shift it up 1, it looks like this. So our new equilibrium is just right here. Again, we tend to prefer our equilibrium to be about 0. Just makes everything simpler. And if we started timing as it crossed the equilibrium, it would look like a sine graph. Because at time 0, it'd be about the center axis, and this would be moving to the right because it's going positive, right? We would time it as it's going this way. Okay. So that's position. Now I want to do something here. 3 is a fine amplitude. We can leave that. But I want to go back into setting omega equal to 1. Ooh, change our frequency though back to 1 instead of 0.2. Okay. So we're just going to say, we're going to just use a sign. So we'll say x of t is the amplitude sine omega t. Equilibrium at 0. So it starts at 0. Actually, I want to do cosine. We're gonna do cosine. Yeah, so we're gonna change this to cosine. Okay, so let's draw our little picture again. This is x is 0. Okay. When I let go, right, it's over here. We start over here. What direction is the velocity going to be in? I let go, it's going to start moving this direction. So our velocity is going to be pointed to the left. So what that's going to look like is we're going to start off with a negative velocity. And really, I mean, you can do this by taking the derivative. This would just be a omega, or minus. That's just the time derivative. Just remember your rules and all that stuff. Looks something like that. So we can plot that velocity. Right. So it looks like a negative sine graph. Same amplitude, because omega here is 1. We set omega equal to 1 this time, not just the frequency equal to 1. So our angular frequency is equal to 1. Otherwise, this would have a higher amplitude, because this number would go up, increase it every time we took the derivative. So if we start here, remember this is our position graph, this is our velocity graph. It's going to be moving to the left, increasing amounts. Then as this is our position, remember, it crosses the origin here, it's going to start moving back up. It's still going to the left, but it's slowing down until it reaches, this is over here, right? So when this is at negative a, over here, it's slowing down, the velocity is 0. And then it starts speeding back up until it crosses the equilibrium. And then we start slowing back down. And likewise, we can find the acceleration, just taking the derivative again. Again, omega is 1 in this case. So our acceleration graph is going to look like this, the green. So now if omega changed every time, so if our frequency was 1, these amplitudes on this graph would go up by a factor of 2 pi every time, because omega is 2 pi f. So let's just look at that real quick. See, the blue is our position, the yellow-orange is our velocity, and the acceleration is the green. It's harder to see though because they're so different. the velocity would go up by a factor of 2 pi, and the acceleration compared to the position would be up by a factor of 4 pi squared. K omega squared. So that's pretty much plotting in a nutshell. You need to be able to look at any one of these. I know that over here it says position, but really the blue's only position. That should say position or velocity or acceleration. Whenever you see, so this is simple harmonic motion. We're going to talk about waves as well, but that's not going to have a time axis. That's going to be a distance x-axis, and we'll get into that probably next week. But for this, these graphs, if you see a position graph, or even these velocity graphs, so if you think about it, let's see. So we're plotting omega. Okay, so if you look, oh my gosh. So 2 pi is our, goodness, period. There you go. Even the acceleration and the, again, this is cut off a little bit over here, and the velocity both have that same period. The period is not going to change. The frequency is not going to change on any of these graphs. They're just shifted over a little bit. And the amplitude would change if omega did change as well, if omega wasn't 1. So, okay, so keep that in mind. So on all the graphs, frequency slash omega is going to be the same, or slash period. What can change, the amplitude is a position thing. So I would say that amplitude doesn't change, but on the graphs it'll change by a factor of 2 pi every time. And it'll be shifted. It'll have this, the phase shift is different for X, V, and A. So you should be able to, what you have to be able to do is find, really any of these variables by reading any of these graphs, position, velocity, or acceleration versus time. That's what you need to be able to do. That's what you need to take away from this. And you need to be able to plot it, because I will test you on that. So I will show you, and we just talked about spring of mass, but I should be able to show you where it starts. Maybe it starts compressed. If it started compressed, then the starting position would be down here. If I show you a spring and mass system, you need to be able to plot all three of these variables. You need to be able to calculate all of these variables. And same goes for a pendulum. We just talked about spring and mass, but for a pendulum, the amplitude, we say this is 0, so theta is 0 here. And then this is our amplitude. And this would be, our negative amplitude. Same thing, just instead of meters, that's why it says meters or angle, it'd be your angle in radians is what we're going to do. We're going to deal with radians. So yeah, if I show you a system, you got to be able to plot it. You got to be able to read these plots and find these variables. Yeah, that's it for now.